In this video, we are discussing the types of loads that can be applied to an object. And in this first slide, I'm reminding you of the difference between a force and a moment. So a force is like written here. It's a force applied at a point in the object that pushes on that object in a given direction. And so the direction is indicated by the x, y, and z components of the force, and so it's a force vector. Now, a moment results when you apply a force at a location different from an origin. So here, there is an r vector from an origin that you can pick, and there's no right origin on an object. It's just saying, given this location, if we're asking about this location, then how is the force applied? And this is especially relevant if you imagine that you come and you hold the object. So you hold the object with your hand at this location so that or another way to think of it is if you stick like a pin through that object at the origin. So if you're holding that object at the origin, and now you want to ask when that red force is applied, what does that do to the object? So because it applies a moment, that it will cause that object to spin around that position. And we'll actually in the second day of class, we'll have some little bars that we can use to show examples of some of this in a demo. So it's easier to see in real life in an object that you're actually pulling on than in a piece of a screen like this. So that's a moment, and you've probably remember these terms, that the moment is here the cross product of the r and the force vector, which is the same as saying the r vector times the f vector, which is the same thing as saying r times f, the magnitude of the distance and the force, times the angle between them, times a unit vector. And that unit vector, that's what that n means, is in and out of the screen in this case. So it's perpendicular to the plane in which r and f lie. And what that means is that's the axis of rotation. So just like I had drawn, like the n vector will be along that line. It's that axis of rotation perpendicular to the plane. And so that's what it rotates around. That n vector is positive. We use the right-hand rule, so we take the r vector from the base of our hand to the joint there. We can do the same thing here. That's our r vector. Then we draw the f vector from the finger to the hands, and so this is explaining how I've lined the hands up here to match this diagram. So, and then given this other diagram, we had to do the same thing, align those parts of our hands up. We see that this is our right hand. Right here, this thumb here is pointing up, so that's out of the plane, and here it's pointing downward into the plane, so that's a negative. So that's the n vector is positive, and here the n vector is negative. And that's what those mean. So you can also calculate these by using the difference between the force vector and the r vector, the sign of that. And so that's that moment is that. Here we just defined it as theta, but that's where it comes from. It's those difference. Another distinction we can make is between concentrated loads and distributed loads. And in this screen, we explain how these differ for forces. So a concentrated load is what we saw, where there is a force applied at a specific location in a specific direction, and so it's concentrated at one position, on the object. But a linearly distributed load is one where there's a object like that, and then we have a force distributed along that object. And it could be uniform or non-uniform. This one is uniform because the force always looks the same. And in this case, we can replace the distributed force with a resultant force. So that distributed force was in units of Newton per meters. The resultant force is in units of newtons because we have integrated over the distance, and that adds a distance unit. So the divided by meters disappears. So that we call that the resultant force, and the location of the resultant force along, in this case, this is like an x direction. The location will be this xr, and that is the integral of the force density function, FD, which was what those little red distributed arrows are, times that x integrated over the distance and then divided by the resultant force. So we have similar expressions that describe if we have a surface where the distributed load, which is now in newtons per meter squared, that FD is distributed over a surface. And similarly, if we have a body force where everywhere inside and outside, not just on the surface, but everywhere inside, so it's a full three-dimensional volume, is subjected to some sort of force. The most common cause, and in that case, that resultant force is in newtons per meters cubed. The most common cause of this is gravitational attraction, and so it depends on the mass density of the object, which is why one way to do these is to calculate by the mass density for those. So these surface and body ones, we just have two-dimensional and three-dimensional integrals, which if those aren't familiar to you, you should go back and look at that and remember that from calculus. It's just fine to do review. We often need review, but I won't always do the reviews in the class when there's something from a prior class. So these are all different types of distributed loads, and they can often, for the ease of calculations, be replaced by these resultant forces and resultant positions. Notably, in the resultant position for this, we need the x, the r, and the y r in two dimensions, and we need all three, also the z r resultant z position for the body force. This example illustrates how we can calculate a resultant force and position from a distributed load. The example is about a cilia, which is an organelle that sticks up from a cell into flowing fluid, such as off an endothelial cell into the blood. And cilia sense fluid flow. We'll learn about them again when we talk about mechanotransduction. The force density here is FD equals a constant C times gamma, the shear rate, times Y, the distance up here from the cell. And that drag coefficient depends on the fluid viscosity and the cross-sectional geometry of the cilia. And so we're going to try to find the resultant force using the formula here that we had in the last slide. And we plug in, this should be C, we plug in the value here for force density, and then we calculate that. So we can pull out the constants from the integration to get the integral of y dy, and that goes from L is 0 down here, or y is 0 down here, to L up there. And so that is y squared over 2 is that integral calculated from 0 to L, which will just equal C times gamma times L squared over 2. So that's the resultant force. And the location of the resultant force, we now have an integral that includes that little y in there. Otherwise, it's like the one above. So we now have y squared dy because we've added that y. And so again, this is C times gamma, but this times it's y cubed over 3, again from 0 to L, and again that 0 gives us nothing to subtract. It ends up being 0, but we have L cubed over 3. But now what I hadn't written in is that we're dividing this by the resultant force. And so when we divide that by the resultant force, oops, that's over 2, we end up with those, everything cancels, but there's a 2 on top, a 3 on the bottom, and a L, so 2/3 L. So that tells us that 2/3 of the way up here, we have the concentrated force. So this here is 2/3 L. That's Y is equal to that value. And the total amount is C gamma L squared over 2. I'll briefly touch on some shortcuts that we can do here. For a symmetric load, the resultant load always acts at the midpoint. So, and another shortcut is that in one dimension, you can draw the shape of the load like I just did here. That was a triangle. We saw that in the previous slide. And the resultant force is the area, and the location is the centroid. So the area of a triangle is 1/2 base times height. And here the base was the force density at the top, which is force density times, and it's at the top because that's the wide end of the triangle. Base refers to the wide end, not the bottom. So force density there would be the C times gamma times L, because Y is L, so this is 1/2 C times gamma times L, and then the triangle height is L again, and so that's C gamma L squared over 2. And you'll see immediately that that was a much quicker calculation than we did on the last slide. So this is the advantage of using that geometry. And then the centroid of a triangle, you may recall, is 1/3 of the distance from the wide end. So if we go up here 1/3, so that this is L over 3 and this is 2L over 3. And it doesn't matter here, but you could also do the centroid as 1/3 across that distance. But this one is the one we really cared about, this location here. And you see that that was at 2, sorry, that was kind of hard to read. That should have said 2/3 L, was at 2/3 L, which is exactly what we found on the previous one. So YR is 2/3 L. So again, use these shortcuts. If you have the information or can look up information on centroid, if you can calculate area, you have lots of tools to do that. And remember, I said that these integrals really are what we've seen before for area. So that makes sense. There's some other shortcuts that we talk about for complex shapes on an additional video that goes over some other calculations like this.